What if I told you that the best AI models in the world don't work alone? That the secret behind the smartest predictions, from Netflix recommendations to life-saving medical diagnoses, isn't just one genius algorithm, but an army of models working together? That's exactly what Ensemble Learning does. And trust me, once you understand it, you'll start seeing it everywhere. In this video, you're going to learn how AI stacks models like building blocks to create something way more powerful than any single system could ever be. We're diving into how banks stop fraud before it happens, how AI predicts the stock market, and even how hospitals use machine learning to detect diseases before symptoms even show up. It's the difference between guessing and knowing. And here's the wild part. Some of the biggest AI breakthroughs, the ones winning Kaggle competitions and driving billion-dollar decisions, all rely on this one technique. If you want to understand the real magic behind AI, you're in the right place. But before we get into it, make sure to hit that subscribe button. This channel is all about breaking down the tech that's shaping our world in a way that actually makes sense. If you want to stay ahead of the AI revolution, stick around. Imagine you're trying to solve a complex puzzle like predicting next week's weather or diagnosing a rare disease. You start with one expert, maybe someone who knows a lot about climate patterns or a doctor specializing in rare illnesses. They're good, but they miss details now and then. Now, imagine you assemble a team of experts, each one focusing on different parts of the problem, like temperature trends, humidity, or a patient's genetics and medical history. Together, they paint a complete picture, far more accurate than any one person could on their own. That's Ensemble Learning in a nutshell. Ensemble Learning is like building the dream team of machine learning models. It's not about relying on a single algorithm to get things right. Instead, it's about combining multiple models, each bringing its unique strengths to the table. Some models are great at catching big trends, while others focus on the fine details. When you put them together, their combined predictions are far more accurate, reliable, and robust. This is where the magic happens. Ensemble Learning takes what might seem like a weakness, one model's limited perspective, and transforms it into a strength by adding diversity. It's like having a jury deliberate on a tough case. One juror might focus on the facts, another might have great instincts, and another might pick up on emotional cues. Their collective decision is almost always better than what any one person could decide alone. In machine learning, this approach is a game changer. It's why ensemble methods have powered some of the most innovative applications in AI. From predicting stock market trends with higher precision to diagnosing diseases before symptoms appear, ensemble learning is shaping the way technology impacts our lives. It doesn't just improve accuracy, it creates systems that are adaptable and resilient, even when faced with messy real-world data. Think of ensemble learning as the backbone of modern AI, a technique that's as much about strategy as it is about computation. By the end of this video, you'll see why it's not just a tool for data scientists, it's a way of thinking about problems that can transform how we tackle challenges in any field. So buckle up. We're about to dive into the fascinating world of ensemble learning and discover why it's the secret weapon behind some of the most powerful AI systems in the world. Have you ever wondered why some sports teams seem unbeatable? It's not because they rely on just one superstar, it's because they have a lineup of players, each with a specific role, attackers, defenders, and playmakers, all working together. Ensemble learning works the same way. It's not just one algorithm calling the shots, it's a team of models, each designed to tackle a specific aspect of the problem. And just like in sports, the way you build and manage your team can completely change the outcome. Now, here's the fun part. Ensemble learning doesn't have one way of working. It has three major strategies, each like a different playbook for building that perfect team. The first playbook is called bagging or bootstrap aggregating. Bagging is the defender of the group, the one that steps in to make sure the team stays stable and avoids wild swings in performance. Think of it like this. Instead of relying on just one decision maker, you ask a whole group for their opinions. Bagging takes random subsets of data, trains individual models on each, and then combines their results to produce a stable, average prediction. It's all about reducing variance, so the predictions don't jump around too much. Random forest, one of the most famous algorithms out there, is the poster child of bagging. This technique shines when you have models prone to overreacting, like decision trees. The second playbook is boosting, and this one's a relentless coach. It doesn't just combine models, it actively pushes each one to get better. Here's how. Boosting trains models sequentially, and each new model focuses on fixing the mistakes of the previous one. It's like running drills over and over until the team stops making the same errors. Weak learners, like shallow trees, are turned into strong ones by constantly refining their focus. Techniques like Adaboost and gradient boosting have revolutionized industries like finance and healthcare because they're so effective at learning from the toughest challenges in the data. And then we have stacking, the master strategist. Stacking is all about bringing together diverse talents. It combines models that think differently, like decision trees, neural networks, and support vector machines, and then trains a meta model to decide how to best blend their predictions. Imagine a conductor leading an orchestra where each musician plays a different instrument, but together they create a masterpiece. Stacking works incredibly well for complex, messy problems where no single model has all the answers. Bagging, boosting, and stacking. Each method has its own unique strengths, and choosing the right one depends on the problem you're trying to solve. But here's the big question. How do you know which one to use and when? Is it always a matter of trial and error, or is there a strategy behind choosing the perfect ensemble method? We're about to find out. Stick with me as we dive deeper into each of these methods and see how they transform raw data into game-changing predictions. Let's break it down step by step. Imagine you're throwing a dart at a target blindfolded. Your chances of hitting the bullseye are slim, right? Now imagine you have 10 friends, each taking a shot, and you average out where the darts land. Suddenly you're much closer to the bullseye. That's bagging in action. Taking multiple attempts, each slightly different, and combining them to get a result that's more accurate and reliable. Bagging, short for bootstrap aggregating, is like having a safety net for predictions. It's designed to reduce the risk of your model going off course by using diversity and collaboration. Here's how it works. Instead of training just one model, bagging trains several models on random subsets of your data. These subsets are created by sampling with replacement, so each model gets a unique view of the data. Once trained, their predictions are combined, usually by averaging for regression tasks or voting for classification. This approach evens out the highs and lows, creating a final model that's far more stable and less prone to overfitting. The star player of bagging is random forest. Think of random forest as a crowd of decision trees, each trained on slightly different data and making slightly different predictions. When these trees vote on the final outcome, the forest produces a result that's more robust and less biased than any single tree could manage. This makes it perfect for problems where individual models are prone to high variance, like decision trees that might overfit the training data. Bagging doesn't just stabilize predictions, it also makes models more resilient to noise. Imagine you're analyzing customer behavior for a marketing campaign. Without bagging, a single outlier, like a customer who bought an unusually high number of products, might skew your predictions. But with bagging, the influence of outliers is diluted, creating a model that reflects the broader trends more accurately. But here's the catch. Bagging works best when your individual models, or weak learners, have high variance. It smooths out their overreactions by letting the team decide. If your models are already stable and low variance, bagging might not add much value. So the big question is, how do you know when bagging is the right choice? And what happens when you need more than just stability? When you need to tackle bias head on? Stay with me, because in the next section, we're stepping into the world of boosting, where models don't just work together, they learn from their mistakes to become stronger. Let's see how boosting turns weak learners into powerhouses. Imagine you're preparing for an exam, but your first attempt at studying leaves you with gaps in your knowledge. You miss key concepts, and it shows in your practice test results. Now, instead of giving up, you focus on those weak spots, studying them more intensely the next time around. This process repeats, and with each cycle, you fill in more gaps and improve your score. That's the essence of boosting. It's not just learning, it's learning smarter by focusing on mistakes. Boosting is all about turning weaknesses into strengths. Unlike bagging, where models work independently and their results are averaged, boosting takes a more disciplined, step-by-step approach. Each model learns from the errors of the previous one, fine-tuning itself to correct what went wrong. By the end of the process, the combined models create a super learner that's stronger than any individual model could ever be. Here's how it works. Boosting starts with a weak model, something simple like a shallow decision tree. It trains this model on the data, but instead of stopping there, it pays extra attention to the mistakes this model made. The next model in line focuses on those errors, giving more weight to the misclassified examples. This process repeats, each model improving upon the last until the final combined model can handle even the toughest patterns in the data. One of the most famous boosting techniques is Adaboost, short for adaptive boosting. Think of Adaboost as the relentless coach that doesn't let you rest until you've nailed every drill. By assigning weights to data points and focusing on the hardest ones, Adaboost builds a strong, cohesive model. Another powerhouse is gradient boosting, which takes things a step further by using gradient descent to optimize its learning process. And then there's XGBoost, the algorithm that's been dominating machine learning competitions thanks to its speed and ability to handle huge data sets. Boosting shines in scenarios where precision matters. In finance, for example, it's used to predict credit scores and detect fraud, focusing on those subtle, high-risk cases that other models might miss. In healthcare, it helps predict patient outcomes by learning from even the smallest patterns in medical data. It's not about getting things right the first time. It's about building a system that keeps learning until it's virtually unbeatable. But here's the twist. Boosting can be a double-edged sword. By focusing so intently on the data, it risks overfitting, especially with noisy data sets. It's like studying so hard for a specific type of question that you miss the bigger picture. So, how do you strike the balance? How do you harness boosting's power without falling into its traps? In the next section, we'll look at stacking, the ensemble method that takes collaboration to a whole new level. Instead of focusing on one type of model, it combines the best of many, creating a strategy that's both flexible and powerful. Let's see how it works. Have you ever watched a heist movie where each member of the team has a specialized role? There's the tech genius, the safecracker, and the smooth-talking con artist. None of them could pull off the job alone, but together their combined skills make them unstoppable. That's what stacking is all about. It's the ultimate team-up, where different models, each with unique strengths, come together to tackle complex problems in ways no single model could. Welcome to the new era of video creation with Jog AI. Simply type your script to get started. Stacking, also known as stacked generalization, is like conducting an orchestra of machine learning models. Each model focuses on a different aspect of the data. One might excel at capturing patterns, another might be great at identifying outliers, and a third might have a talent for spotting trends. But here's the twist. The real magic happens when a meta model steps in. This meta model takes the predictions from all these base models and learns how to combine them in the smartest possible way, creating a final output that's greater than the sum of its parts. Let's break it down. First, you train several base models. These could be anything from decision trees to neural networks, each working on the same problem but interpreting the data in its own unique way. Once these models make their predictions, the metamodel steps in. Using these predictions as input features, the metamodel is trained on a validation set to figure out how to best blend the contributions of the base models. It's like having a captain on a sports team who knows how to coordinate every player's strengths to score the winning goal. Stacking is incredibly flexible because it doesn't limit you to one type of model. You can mix and match different algorithms, combining their unique perspectives to create a well-rounded, high-performing ensemble. For instance, a stacking setup might include a decision tree for structure, a support vector machine for precision, and a neural network for capturing complex relationships. The result, a powerful system that can adapt to just about any challenge. Where does stacking shine? It's a favorite in high-stakes environments like Kaggle competitions, where even a 1% improvement in accuracy can make the difference between first place and obscurity. But it's not just for competitions. In finance, stacking is used for credit scoring by combining the strengths of different models to predict risk more accurately. In healthcare, it's used to integrate data from various sources like genetic profiles, medical records, and imaging results to improve diagnostic accuracy by up to 10-25%. But here's the thing. Stacking isn't just about throwing models together and hoping for the best. It requires careful planning to avoid overfitting, and the choice of base models and the meta model can make or break the results. So, how do you design the perfect stack? And what happens when the models themselves disagree? That's what we'll explore as we move deeper into the world of ensemble learning. The next step? Comparing these methods, bagging, boosting, and stacking, and understanding how to choose the right one for your specific problem. Stay with me, because this is where everything starts coming together. Imagine you're a coach building a team for an upcoming championship. You've got two strategies. In the first, you assemble a group of players, each with their strengths and weaknesses, and let them work independently. At the end, you combine their scores to determine the winner. This strategy ensures stability. It evens out the highs and lows, making sure your team is consistent. That's bagging. Now, in the second strategy, you start with a small group of players, but instead of letting them work independently, you push each one to learn from their mistakes after every round. Each new player trains harder, focusing on what the last one got wrong. By the end, you've built a powerhouse team where every player is sharper and better prepared. That's boosting. Bagging and boosting are both ensemble methods, but they approach the problem in fundamentally different ways. Bagging is like building a safety net. It trains multiple models independently on different subsets of your data, and their predictions are averaged or voted on to get a final result. This reduces variance and makes the model less likely to overfit. Think of random forest, the shining star of bagging, which uses this method to create stable, reliable predictions that work wonders in noisy or high variance scenarios. Boosting, on the other hand, is all about learning from mistakes. It's an iterative process where each model is trained to fix the errors of the previous one. This makes boosting particularly powerful for reducing bias and improving accuracy. Algorithms like Adaboost and gradient boosting take weak learners like shallow decision trees and turn them into strong, focused predictors. They're like relentless personal trainers, never letting up until the model is as accurate as possible. But here's the catch. Bagging and boosting aren't interchangeable. They're designed for different kinds of problems. Bagging works best when you're dealing with high variance models, where predictions might fluctuate wildly. It stabilizes and strengthens the model, making it a perfect choice for scenarios where consistency is key. Boosting, on the other hand, is the go-to method when you're facing high bias problems, where the model might be too simplistic to capture the full complexity of the data. It digs deep, refining and improving until the model gets it right. So how do you choose between the two? Well, it depends on your goals. Do you need a system that's stable and robust against noise? Go for bagging. Are you looking to squeeze every ounce of accuracy out of your model? Boosting's your best bet. But what if your problem requires both? What if you need a solution that's not just accurate, but also flexible enough to adapt to changing data? That's where the real power of ensemble learning lies, understanding these methods, knowing when to use them, and even combining their strengths. Stick with me, because next we'll dive into the practical advantages and challenges of ensemble methods, and you'll see just how transformative they can be. Why do we turn to ensemble methods in the first place? Let me paint a picture for you. Imagine you're trying to solve a puzzle with blurry pieces. One person can barely make out the edges, another sees some details in the center, and a third notices the colors. None of them alone can complete the picture, but when they work together, suddenly the puzzle becomes clear. That's the power of ensemble learning. It pieces together strengths to create something far greater than any single model could achieve. First and foremost, ensemble methods are all about accuracy. They're not satisfied with good enough. By combining multiple models, ensemble learning delivers predictions that are significantly more precise. In fact, studies show that ensembles can improve accuracy by as much as 10 to 20% compared to individual models. That might not sound like a lot, but in industries like finance, healthcare, or autonomous driving, even a 1% improvement can mean the difference between success and failure. It's like upgrading from a blurry snapshot to crystal clear HD. But accuracy isn't the only benefit. Ensembles are also brilliant at generalization. They perform well not just on the data they've seen before, but also on new, unseen data. This is because the diversity among the models allows the ensemble to capture a wider range of patterns, making it adaptable to different scenarios. It's like having a team of experts, each with their own perspective, ensuring nothing important gets missed. And then there's robustness. Every model has weaknesses, but by combining their outputs, ensemble methods reduce the risk of overfitting to the quirks of the training data. This makes them ideal for real-world applications where the data is often messy, incomplete, or noisy. Think of it as having a backup plan. If one model makes a mistake, the others can step in to correct it. Ensemble methods also offer incredible flexibility. They don't tie you down to one type of model, whether you're working with decision trees, neural networks, or support vector machines. Ensembles let you mix and match to create the best possible solution. It's like having the freedom to build your dream team from any league without being restricted to just one sport. But let's take a moment to reflect on what this really means. Ensemble methods aren't just algorithms, they're a mindset. They teach us that diversity and collaboration often lead to better outcomes. They show us the importance of balancing strengths and weaknesses, of combining different perspectives to tackle complex problems. Here's the question though, if ensemble methods are so powerful, why aren't they used for every problem? What's the catch? To truly understand their potential, we need to look at the challenges they bring: complexity, interpretability, and computational costs. Let's explore these hurdles in the next section and see how they shape the way we use ensembles in practice. If ensemble methods are so powerful, why doesn't everyone use them all the time? The truth is, even the best tools come with their own set of challenges. It's like driving a high-performance sports car. Sure, it's fast and exciting, but it also comes with higher maintenance costs and requires a skilled driver. Ensemble learning is no different. It's a powerhouse technique, but it demands careful handling. Let's start with computational complexity. Think about it. When you're using multiple models instead of one, you're naturally going to need more resources. Training a single decision tree is relatively fast, but now imagine training hundreds of them, like in a random forest, or training sequential models one after the other in boosting. The time and computational power required can multiply quickly. It's like moving from cooking a simple meal for one person to catering a banquet. It's a whole new level of effort. Then there's the issue of interpretability. One of the great things about a single decision tree is that it's easy to understand. You can visualize the splits and see exactly how it made its decisions. But when you start combining models into an ensemble, the simplicity disappears. Suddenly, you're dealing with a black box where understanding why the model made a specific prediction becomes much harder. This lack of transparency can be a problem, especially in fields like healthcare or finance, where decision-making needs to be explainable. Another challenge is overfitting. Wait, didn't we just say ensembles are great at reducing overfitting? Yes, they are, when designed correctly. But here's the thing. If your base models are too complex or your ensemble isn't tuned properly, you can end up overfitting anyway. It's like using too many cooks in the kitchen. At some point, they start stepping on each other's toes, and the dish doesn't turn out as planned. And let's not forget about the sheer complexity of managing an ensemble. Choosing the right base models, balancing their contributions, tuning hyperparameters, it's a lot. It's no longer just about building a single great model. It's about orchestrating a system of models that work in harmony, and that requires expertise, time, and patience. But here's the thing. These challenges aren't deal breakers. They're puzzles to be solved. And when you solve them, the payoff is immense. Ensembles are still the go-to choice for some of the toughest problems in machine learning, precisely because their strengths outweigh their challenges. So how do we overcome these hurdles? How do we balance complexity and interpretability, or power through the computational demands? That's where the art of ensemble learning comes in, knowing how to apply these methods in a way that gets results without falling into their traps. And in the next section, we'll look at specific case studies where ensembles have tackled real-world challenges, proving their worth in action. Stay tuned. Imagine walking into a forest. Every tree is unique, yet together they form a system that's balanced, robust, and full of life. That's exactly how random forest works. It's not just a single decision tree. It's an ensemble of many, each trained on slightly different data, working together to create predictions that are far more accurate and reliable. Random forest is the crown jewel of bagging techniques, and it has earned its reputation as one of the most versatile and powerful algorithms in machine learning. So, how does it work? Random forest starts by building multiple decision trees, each trained on a random subset of the training data. But it doesn't stop there. At each split within those trees, it randomly selects a subset of features to consider. This randomness ensures that the trees don't all end up looking the same and capturing the same patterns. In other words, it promotes diversity, and that diversity is what makes the ensemble so strong. Once all the trees are built, they vote on the final prediction. For classification problems, it's a majority vote. Whichever class most trees predict is the result. For regression tasks, it takes the average of all the predictions. This process reduces overfitting and smooths out the quirks that any single tree might have, creating a model that's both accurate and robust. Now, let's talk about why random forest is such a game changer. First, it's incredibly versatile. Whether you're predicting loan defaults in finance, diagnosing diseases in healthcare, or segmenting customers in marketing, random forest can handle it all. It's particularly useful when you're dealing with datasets that are noisy or have a mix of numerical and categorical features. But random forest doesn't just make predictions, it also provides insights. By measuring how much each feature contributes to the accuracy of the model, it can rank feature importance. Imagine you're working on a healthcare problem and you want to know which factors, age, lifestyle, genetics are most critical in predicting a disease. Random forest can give you that answer, helping you focus on what really matters. And let's not forget its resilience. Random forest is naturally resistant to overfitting thanks to its use of bagging and random feature selection. It's like a safety net that catches you even when the data is messy or incomplete. That's why it's often the first algorithm data scientists reach for when they're exploring a new problem. But here's the real kicker. Random forest isn't just a tool for today, it's evolving for the future. Hybrid models that combine random forest with deep learning are being developed to handle even more complex data, and researchers are scaling it for big data applications, making it faster and more efficient. So what's the catch? Well, random forest isn't perfect. Its strength in diversity can sometimes make it harder to interpret, and its computational requirements can be high when dealing with very large data sets. But for all its challenges, the power and flexibility it offers make it a cornerstone of modern machine learning. Now that we've explored how random forest works, let's take it a step further. In the next section, we'll look at boosting techniques like Adaboost, which take a completely different approach to solving problems. Instead of relying on diversity, they focus on learning from their mistakes to create even stronger predictions. Let's see how they compare. Imagine you're training for a marathon, but your first run is a disaster. You're out of breath, your pace is inconsistent, and you barely make it halfway. But instead of giving up, you analyze what went wrong. The next day you focus on breathing. The day after you fix your stride. Little by little you correct your weaknesses until finally you're running smoother, faster, and stronger than ever before. That's Adaboost in action. It doesn't just throw models together, it builds them step by step, constantly learning from mistakes until it creates a predictive powerhouse. Adaboost, short for adaptive boosting, is one of the most famous boosting algorithms, and it works differently from anything we've seen so far. Instead of training all models at once, like in bagging, Adaboost trains models sequentially, where each new model focuses on correcting the errors of the previous one. It's like having a personal coach that pushes you to improve every time you train. Here's how it works. It starts with a weak learner, a simple model like a shallow decision tree. It makes its first set of predictions, but naturally some mistakes happen. The next model is trained, but instead of treating all data points equally, it pays extra attention to the ones that were misclassified in the previous round. The harder to predict examples get higher weights, forcing the next model to work harder on them. This process repeats, with each new model getting smarter, more focused, and more accurate. In the end, all models are combined into a weighted sum, where the best performing ones have the most influence on the final decision. This makes Adaboost incredibly powerful for improving weak models. Even a series of very simple decision trees can be stacked into something far more accurate than a single complex tree. The real magic of Adaboost is that it doesn't just build a strong model. It builds intelligence into the learning process itself by adjusting as it goes. So where is Adaboost used? It shines in scenarios where precision matters most. In fraud detection, for example, where identifying small anomalies is crucial, Adaboost can continuously refine its understanding of what constitutes suspicious behavior. In image classification, it focuses on the most confusing parts of an image, ensuring it captures even the hardest to spot details. And in medicine, it helps diagnose diseases by training itself to pick up on cases that other models might overlook. But here's the thing, Adaboost isn't invincible. It's highly sensitive to noise because it puts so much emphasis on correcting mistakes. If your dataset has a lot of outliers, Adaboost might spend too much time trying to fit them, which can actually reduce its overall performance. It's also more computationally expensive than simpler models because it keeps refining itself step by step. So, is Adaboost always the right choice? Not necessarily. It's great when you need high accuracy and can afford the extra training time, but in cases where speed or stability is more important, other methods might be better. But what if we took this idea of boosting and pushed it to the extreme? What if we built an even more optimized version of boosting that could handle massive data sets, work at lightning speed, and dominate machine learning competitions? Well, that's exactly what gradient boosting does, and it's what we're diving into next. Imagine climbing a mountain, but instead of trying to sprint to the top, you take it step by step, carefully analyzing where you slipped and adjusting your path with each step forward. Gradient boosting is like that. It's not about rushing, it's about learning, adapting, and optimizing every move to eventually reach the peak of predictive accuracy. Gradient boosting is one of the most advanced and refined forms of boosting. Like Adaboost, it builds models sequentially, with each new model correcting the errors of the previous one. But here's where it gets more sophisticated. Gradient boosting uses a mathematical technique called gradient descent optimization to minimize errors. It doesn't just identify where the mistakes are, it calculates the direction and size of the corrections needed, creating an incredibly efficient learning process. At its core, gradient boosting often uses decision trees as base learners. These aren't the towering, complex trees we sometimes think of. They're small, shallow trees, also known as stumps. Why stumps? Because they're fast to train, and gradient boosting doesn't rely on individual power. It's about the cumulative strength of many simple models working together. The result? High predictive performance. Gradient boosting isn't just accurate, it's adaptable. Whether you're handling classification or regression tasks, this method fine-tunes itself to match the complexity of the problem. That's why it's become a favorite in real-world applications like credit scoring, risk assessment, and even healthcare diagnostics. Let's look at a real-world example. In finance, gradient boosting has been a game changer for identifying credit risks. By analyzing historical data, it pinpoints patterns that signal potential loan defaults with impressive precision. In healthcare, it's used to predict patient outcomes, helping doctors make better decisions and improving survival rates in critical scenarios. And in marketing, it powers customer segmentation and personalized targeting, increasing engagement and boosting ROI. What makes gradient boosting even more exciting is its flexibility. It can handle different loss functions, making it highly versatile. Plus, it integrates seamlessly with other advanced techniques, laying the groundwork for even more powerful ensemble methods like XGBoost. But here's the big question. How can we push this already incredible method even further? The answer lies in optimizing it for speed and scalability, which is where XGBoost comes into the picture. In the next slide, we'll dive into how XGBoost takes gradient boosting to the next level, dominating competitions and driving innovation. Let's see how it works. Imagine taking a sports car and tuning it to be even faster, sleeker, and more efficient. It's already powerful, but now it dominates the track. That's what XGBoost does for gradient boosting. It's not just an improvement, it's a revolution. XGBoost stands for Extreme Gradient Boosting, and it's become the go-to method for tackling some of the hardest machine learning problems out there. So what makes XGBoost so special? At its core, it still uses the same principle as gradient boosting, building models sequentially, where each one corrects the errors of the previous one. But XGBoost takes optimization to a whole new level. It's designed to be faster, more scalable, and more accurate, making it the ultimate tool for real-world applications and machine learning competitions. Let's break it down. One of XGBoost's biggest strengths is its ability to handle regularization. It uses advanced techniques like L1, lasso, and L2, ridge regularization to prevent overfitting, ensuring the model doesn't just memorize the data, but generalizes well to unseen examples. This is crucial when you're working with messy, noisy, or imbalanced datasets. Then there's its parallel processing capability. Unlike traditional gradient boosting, which processes sequentially and can be slow, XGBoost leverages multi-core CPUs and GPUs to speed up training dramatically. This means it can handle massive data sets in a fraction of the time, making it ideal for industries like finance, healthcare, and e-commerce, where speed and accuracy are critical. And the results speak for themselves. XGBoost has become a champion in Kaggle competitions where data scientists compete to solve complex problems. Its predictive power, combined with its efficiency, has made it a favorite for tasks like credit scoring, fraud detection, and customer behavior analysis. But XGBoost isn't just for competitions, it's a game changer in the real world. In finance, it's used for risk assessment, identifying subtle patterns in credit data that help predict loan defaults. In healthcare, it analyzes patient outcomes, identifying key factors that influence disease progression or treatment success. And in marketing, it powers predictive analytics, helping companies forecast trends and fine-tune their strategies. With all this power, is there a catch? Well, XGBoost's complexity can make it a bit challenging to tune. Getting the most out of it requires careful attention to hyperparameters, such as learning rate, tree depth, and the number of estimators. But for those willing to invest the time, the payoff is enormous. So, what's next? XGBoost is a prime example of how machine learning techniques continue to evolve. And as we look toward the future, new advancements like AutoML and hybrid models are pushing the boundaries even further. But for now, XGBoost remains the gold standard for turning raw data into actionable insights. Stick with me because next we'll explore real-world case studies that show how these methods, bagging, boosting, and stacking, are transforming industries. Let's see these techniques in action. Imagine you're at a brainstorming session with a room full of experts. One person is a data scientist, another is a marketing guru, and another is a finance whiz. Each brings their unique perspective to the table. Alone, they're impressive, but when they combine their insights, they can solve problems faster and more effectively. That's the beauty of stacking, bringing diverse models together to create something stronger than the sum of its parts. Stacking isn't just a theoretical concept, it's being used in the real world to tackle high-stakes challenges. Let's take a look at two industries where stacking is making waves: finance and healthcare. In finance, stacking is revolutionizing how credit scoring systems work. Think about it. Predicting whether someone will default on a loan is no small task. It requires understanding patterns in credit history, income levels, spending habits, and more. By combining models like logistic regression, decision trees, and support vector machines, stacking captures all these perspectives. The result? A 15% improvement in prediction accuracy, leading to better risk assessments and fewer defaults. That's not just good for banks. It's life-changing for borrowers who might otherwise have been overlooked. But it doesn't stop there. Stacking is also transforming algorithmic trading. By merging predictions from multiple trading strategies, it helps optimize buy and sell decisions, leading to an increase in returns. In fact, studies show that stacking can boost returns by up to 20% compared to single strategy approaches. For financial institutions, that's a game changer in a world where every second and every dollar counts. Now, let's shift gears to healthcare, where stacking is saving lives. Disease prediction, for example, is a complex puzzle. It requires analyzing patient data, medical history, genetic information, and even environmental factors. By combining models that specialize in different types of data, stacking delivers more accurate diagnoses, improving prediction accuracy by 10 to 25%. This isn't just about statistics. It means earlier interventions, personalized treatment plans, and better outcomes for patients. Another groundbreaking application is in medical imaging. Stacking combines algorithms to enhance the detection of anomalies in scans, such as tumors. With up to a 30% improvement in sensitivity, doctors can identify life-threatening conditions earlier and more accurately than ever before. What makes stacking so powerful in these applications is its ability to integrate diverse sources of information. It's not locked into one way of thinking. Instead, it pulls together the strengths of multiple approaches, creating solutions that are not just accurate but also adaptable. But here's the question: how do you know when to use stacking? The answer lies in complexity. If your problem involves diverse data or requires predictions from different angles, stacking is your best friend. And as we move into the next section, we'll see how these techniques are implemented step by step in real-world workflows. Let's explore how to take these concepts and put them into practice. Let's bring everything we've talked about so far into focus. Ensemble learning might sound powerful in theory, but how do you actually put it into practice? It's like building a machine. You need the right parts, a clear plan, and some careful assembly. Let me walk you through the 4 key steps of applying ensemble learning from start to finish. Step 1, data preparation. This is where it all begins, and trust me, it's the foundation for everything that comes next. Start by collecting and pre-processing your dataset. Clean the data, handle missing values, normalize or standardize features, and make sure the dataset is balanced if necessary. Then split your data into training and testing sets, usually with an 80-20 ratio. Remember, the quality of your data directly impacts the quality of your ensemble model. It's like cooking. No matter how skilled you are, you can't make a great dish with poor ingredients. Step 2, model selection. Here's where you decide which models will make up your ensemble. Do you want decision trees for their structure, support vector machines for precision, or maybe neural networks for their complexity? The choice depends on your problem. For example, if you're dealing with noisy data, you might lean toward bagging techniques like random forest. If your goal is to reduce bias, boosting methods like gradient boosting might be a better fit. The key is diversity. Select models that complement each other and capture different aspects of the data. Step 3, ensemble method implementation. Now it's time to assemble your machine. If you're using bagging, create multiple subsets of your training data. Train models on each subset and combine their predictions. For boosting, train models sequentially, with each new model focusing on the errors of the previous one. And if you're going for stacking, train multiple base models and then feed their predictions into a meta model. Each method has its own workflow, so the choice depends on your use case and objectives. Step 4, model evaluation. This is the moment of truth. Evaluate your ensemble's performance using metrics like accuracy, precision, recall, and F1 score. Cross-validation is your best friend here. It ensures your model is robust and isn't overfitting to the training data. A common approach is k-fold cross-validation, where the dataset is split into k parts and the model is trained and tested k times, each time with a different fold as the test set. This gives you a reliable estimate of how your ensemble will perform on unseen data. These 4 steps, prepare, select, implement, and evaluate, form the backbone of applying ensemble learning in the real world. But here's the exciting part. Once you master this process, the possibilities are endless. You can tackle complex problems across industries, from predicting disease outcomes in healthcare to optimizing marketing campaigns and even forecasting stock prices. In the next slide, we'll look at some specific case studies that show how these steps come together to solve real-world challenges. From healthcare to finance, you'll see how ensemble learning is making a difference every day. Let's dive in. Let's shift gears and dive into the real world. Imagine a hospital where every decision, every diagnosis, every treatment plan is informed by data. Lives are on the line and the stakes couldn't be higher. This is where ensemble learning steps in, not just as a tool, but as a game changer. In healthcare, ensemble learning methods like random forest and gradient boosting are transforming the way we predict and treat diseases. Why? Because they combine the power of multiple models to provide accurate, data-driven insights. Let me walk you through how this works. Take disease prediction, for example. Diagnosing conditions like diabetes or cardiovascular diseases isn't easy. It requires analyzing mountains of data, patient history, genetic information, lab results, and more. By using ensemble models, healthcare providers can aggregate predictions from multiple algorithms, significantly reducing the risk of overfitting and improving accuracy. In one study, a random forest model achieved an 85% accuracy rate for predicting diabetes onset, outperforming single classifiers by 10%. That's not just a better prediction, that's the potential to save lives. But the impact of ensemble learning doesn't stop at diagnosis. It's also helping with patient outcome analysis. Picture a scenario where a patient has just undergone surgery. Predicting whether they're likely to be readmitted within 30 days can make a huge difference in planning their care. Ensemble models have been used to analyze post-treatment data, reducing readmission rates by up to 15%. This means fewer unnecessary hospital visits, better resource allocation, and ultimately healthier patients. Another breakthrough is in medical imaging. Detecting anomalies like tumors in scans is a complex task, and mistakes can be life-threatening. Ensemble methods combine the strengths of multiple image analysis algorithms, improving sensitivity by up to 30%. That means doctors can catch life-threatening conditions earlier, leading to faster interventions and better outcomes. What's truly inspiring is that ensemble learning isn't just about numbers, it's about empowering healthcare providers to make better decisions. By integrating diverse data sources, it paints a more complete picture of each patient, allowing for personalized treatment plans and more effective care. But here's the challenge. Implementing these methods in healthcare isn't always straightforward. It requires collaboration between data scientists, doctors, and hospital administrators. And of course, the data needs to be clean, secure, and accessible. When done right, though, the results are undeniable. Next, we'll take a look at another field where ensemble learning is making waves: finance. From fraud detection to stock market prediction, these methods are reshaping industries beyond healthcare. Let's see how. Let's move from saving lives in healthcare to saving money and sometimes even entire businesses in the world of finance. In this fast-paced, high-stakes environment where billions of dollars are on the line, ensemble learning is stepping up as the ultimate financial watchdog and decision-making assistant. Take fraud detection, for example. Fraud is like a constantly evolving game of hide and seek. Every time you think you've caught it, the patterns shift, making it harder to track. Traditional single model approaches struggle to keep up with the complexity and speed of modern financial systems. That's where ensemble methods like random forest and gradient boosting come in. These models work by combining insights from multiple algorithms, each trained to detect different patterns in the data. One study showed that using ensemble learning improved fraud detection rates by up to 30% compared to traditional single model approaches. Imagine catching a fraudulent transaction before it even has a chance to process. That's the kind of real-time protection ensemble models provide, significantly reducing financial losses for banks and businesses. Now let's talk about stock market prediction. In this world, accuracy isn't just a luxury, it's a necessity. Predicting stock prices requires analyzing a vast amount of data, from historical trends and market indicators to breaking news and global events. Ensemble learning shines here by combining models like bagging and boosting to make predictions that are both robust and adaptable. Research has shown that ensemble models can reduce prediction errors measured by mean absolute percentage error, MAP, by up to 15% compared to individual models. That means more informed investment decisions and better risk management. For traders and financial institutions, this kind of edge can be the difference between a winning portfolio and a costly misstep. But the beauty of ensemble learning in finance doesn't stop at fraud detection and stock prediction. These techniques are also used for credit scoring, helping lenders identify risks more accurately, and algorithmic trading, where models analyze vast streams of data to optimize buy-sell strategies in real time. Of course, there are challenges. Financial data is often messy, imbalanced, and riddled with noise. And while ensemble methods are powerful, they can be computationally intensive and require careful tuning. But when these hurdles are overcome, the payoff is undeniable. Finance is just one of the many industries harnessing the power of ensemble learning to drive better decisions and stay ahead of the curve. And if you think this is impressive, wait until we dive into marketing, where these methods are transforming how businesses engage with their customers. Let's explore that next. Let's talk about marketing, where understanding your customer can make or break your business. In today's digital-first world, businesses are drowning in data, website clicks, purchase histories, social media activity. But the real question is, how do you turn all that noise into actionable insights? That's where ensemble learning steps in, reshaping how companies connect with their customers. Let's start with customer segmentation. Imagine trying to divide your audience into meaningful groups. Who loves discounts? Who prefers premium experiences? Traditional methods often fall short, missing subtle patterns in the data. Ensemble methods like random forest and gradient boosting take this challenge head-on by combining multiple models to capture the nuances. The result? Improved segmentation accuracy by 25%. This means businesses can craft personalized strategies, leading to higher engagement and better customer satisfaction. But segmentation is just the beginning. Campaign optimization is where things get really exciting. Marketing teams constantly face the challenge of delivering the right message to the right audience at the right time. By integrating predictions from multiple models, ensemble learning helps fine-tune campaigns for maximum impact. In fact, businesses using these techniques have seen a 30% increase in ROI. Think about that. 30% more value from the same campaign just by making smarter, data-driven decisions. And then there's the powerhouse of predictive analytics. Ensemble learning doesn't just help businesses understand their customers. It helps them anticipate what customers will do next. From forecasting, purchasing behavior to managing inventory, these predictions allow companies to stay one step ahead. Studies show that predictive accuracy can improve by 20% when ensemble methods are used, giving businesses the confidence to make bold, proactive moves. The beauty of ensemble learning in marketing is its adaptability. Whether you're launching a new product, fine-tuning a loyalty program, or planning a global campaign, these methods ensure you're always working with the best insights available. It's like having a team of data scientists constantly analyzing every angle for you. But, of course, marketing isn't just about algorithms. It's about storytelling, creativity, and connecting with people. Ensemble learning is the bridge between art and science, allowing marketers to focus on the big picture while the models handle the heavy lifting. Now, as we look ahead, it's clear that ensemble learning is transforming industries across the board. But how do we navigate its strengths and weaknesses to make the most of it? That's what we'll explore in the next section. Let's dive into a SWOT analysis of ensemble learning to see how it fits into the bigger picture. Now that we've seen ensemble learning in action, let's step back and take a 360-degree view of its strengths, weaknesses, opportunities, and threats. This is like a strategy session for deciding how and when to use ensemble learning to maximize its potential while avoiding its pitfalls. Let's start with the strengths, the reasons ensemble learning has become a favorite among data scientists. First and foremost, it delivers improved accuracy by combining multiple models. Techniques like bagging and boosting significantly reduce variance and bias. For example, random forest can improve accuracy by 10–15% compared to a single model. These methods are robust, reliable, and adaptable to a variety of tasks, from healthcare diagnostics to marketing analytics. Another strength is enhanced generalization. Ensemble models excel at making predictions on unseen data because they capture patterns that individual models might miss. This ability to generalize makes them invaluable for real-world applications where the data is often messy and unpredictable. But let's not ignore the weaknesses. One of the biggest challenges is complexity. Integrating multiple models increases computational costs and requires careful tuning of parameters. And with more models in the mix, interpretability often takes a hit. It's harder to explain why an ensemble made a particular prediction, which can be a deal breaker in industries like finance or healthcare, where transparency is key. Now, let's talk about the opportunities. The demand for robust, data-driven decision-making is skyrocketing. As industries increasingly rely on AI, ensemble learning is perfectly positioned to lead the charge. From finance to healthcare, these methods are being leveraged to solve increasingly complex problems. And with advancements in technology, like AutoML and hybrid models, ensemble learning is becoming more accessible to non-experts, opening doors for even broader adoption. But, like any powerful tool, ensemble learning isn't without its threats. The risk of overfitting is real, especially if the ensemble isn't properly designed or if the data is insufficient. Poorly tuned ensembles can end up memorizing the training data rather than learning from it. And then there's the issue of computational demands. Deploying ensemble models in resource-constrained environments can be a real challenge. So where does that leave us? Ensemble learning is a powerhouse, but it's not a magic wand. It requires careful planning, expert tuning, and a clear understanding of the problem at hand. When used wisely, it can deliver transformative results across industries. But like any strategy, it's essential to weigh the pros and cons before diving in. In the next slide, we'll look at the future of ensemble learning and how advancements in algorithms and technology are pushing the boundaries even further. Let's explore what's on the horizon. What's next for ensemble learning? If you think it's impressive now, just wait. The future of ensemble learning is unfolding right before us, and it's full of exciting advancements that are set to push boundaries and redefine what's possible in machine learning. Let's start with advancements in algorithms. Imagine combining the best of traditional ensemble methods with the power of deep learning. That's exactly what hybrid models aim to do. By blending techniques like stacking and boosting with neural networks, these models are poised to unlock new levels of accuracy and flexibility. They'll allow us to handle more complex data, extract deeper insights, and apply ensemble learning in ways we haven't even imagined yet. Another game changer is automated machine learning, or AutoML. AutoML frameworks are already making ensemble learning more accessible by automating the selection, tuning, and optimization of models. In the future, even non-experts will be able to deploy powerful ensemble solutions with just a few clicks. This democratization of AI could lead to a massive wave of innovation, empowering small businesses, researchers, and educators to tackle problems previously out of their reach. But algorithms alone won't shape the future. The rise of cloud computing and parallel processing is already supercharging ensemble learning. With the accessibility of platforms like GPUs, TPUs, and distributed cloud environments, we'll be able to train massive ensemble models on enormous datasets in a fraction of the time. This will make real-time predictions not just possible but practical, whether it's for fraud detection in finance, disease prediction in healthcare, or customer analytics in marketing. And let's not forget the real-world applications. Healthcare, finance, and marketing will continue to lead the charge, but new fields are emerging. Imagine using ensemble learning to optimize renewable energy grids, manage supply chains more effectively, or even tackle climate change by predicting environmental shifts. The versatility of these methods means the possibilities are endless. However, the future isn't without its challenges. With increased computational power comes the risk of greater complexity. Models will need to be carefully designed to avoid becoming black boxes that are difficult to interpret. And as ensemble learning spreads to more industries, ethical considerations like data privacy and bias will demand our attention. So, where does this leave us? The future of ensemble learning is about more than just better predictions. It's about building systems that are faster, smarter, and more adaptable. Tools that can tackle humanity's most complex challenges while remaining accessible and ethical. In the final slide, we'll wrap everything up with a summary of what we've learned and the key takeaways from this journey through ensemble learning. Let's bring it all together. We've covered a lot in this journey through ensemble learning, and now it's time to bring it all together. If there's one thing to take away, it's this: the best models don't work alone. Just like a championship-winning team, ensemble methods combine strengths, reduce weaknesses, and deliver performance that no single model can achieve on its own. We started with the core idea of ensemble learning, how combining multiple models leads to stronger, more accurate, and more reliable predictions. From there, we explored the three major techniques: bagging, which reduces variance and stabilizes models like random forest; boosting, which learns from mistakes and turns weak models into powerful predictors, as seen in Adaboost; and gradient boosting, stacking, the master strategist that blends different models for optimal decision-making. Then we saw real-world impact, from predicting diseases in healthcare to detecting fraud in finance. From optimizing marketing campaigns to forecasting stock trends, ensemble learning isn't just theory, it's actively transforming industries. We also weighed the pros and cons. While ensemble methods bring improved accuracy, robustness, and generalization, they also come with challenges like complexity, computational cost, and potential overfitting. But as we saw, the opportunities far outweigh the risks, especially with advancements in AutoML, hybrid models, and parallel computing making ensemble learning more efficient and accessible than ever. So, where do we go from here? The future of ensemble learning is bright and it's evolving fast. Whether you're a data scientist, a business leader, or just someone curious about AI, one thing is clear: ensemble learning is shaping the future of machine learning. And now you understand why. If you found this valuable, let's keep the conversation going. Drop a comment, ask a question, or share your thoughts. And of course, if you haven't yet, hit that subscribe button so you don't miss out on more insights into the world of AI and machine learning. Thank you for joining me on this journey. Until next time, stay curious, stay innovative, and I'll see you in the next video.